Okay, so what we have here is we want to assemble k global, k local. So we're going to have essentially local indexes and the element number. And we need to ask ourselves what we want to use what for. So essentially, we're going to infer the global coordinate number based on what the element number is. So if you imagine, if you draw down here element, let me just draw it like star, star, star. So let's say this is my element, so 2 elements that we've done before, and I'm going to number this 1. Oh, this is working quite well. 2, 3, 4, 5. Make sure everything's recording. Okay, that's fine. Okay, so that's essentially that. And what we are going to infer here is the following: to say, take the element number. So let's say if my element number is element 0, then what I'm going to do is I'm going to take that element number multiplied by 2 and plus j, and j will go always from 1 to 3. So the element number, if I'm working with element number 0, j will essentially start from 0 to 2. It will run from 0 to 2, and that is essentially what we have there. So this element numbers 0, 1, 2 for the indexes, although the numbering you might want to call it 1 to 3 if you want, or you can also call it 0, 1, 2 if you want. But that's essentially what that global will do for us. This j global, and this k global is essentially this one that we are computing here. So this is just the k index global version of that, and that's following the same argument that essentially we want to run over the range of indexes for that element. Okay, so this will do same range as what this would do. As this index runs over the rows, this index runs over the columns, this k. Okay, so that allows us to access the global numbering. Okay, so we can see if it will work for the second element. If I make element number 1, so it's 2 times 1, okay, plus 0 in the beginning, and so it will have index number 2, which is that one. Then it will be index number 3, then index number 4 as the outer loop runs. And same for the inside loop, it will be 2, 3, 4. So this is essentially giving us a good idea of what the indexes are. And then for each element, we'll just add it in. So you can imagine this, we add in the next one, and the next one. So instead of coding the element numbers, we just infer it. And this is what this is doing. Okay, so just a Jipper way, and explicitly giving a list of saying this is the position, the x coordinate, and the node number. We're just inferring the node number. So if I look at the third element, I would like it to start at index 4, and then 5 and 6. The third element is 2 times 3. Okay, so that's essentially what we have there. What did I? Yeah, so third element, but remember we had elements number 2. Wait, what is going on here? 1, 2, 3, 4, 5, 6, 7. Yeah. So that's fine. So we wanted to have index 4, 5, and 6. So anyway, if it's a third element, it's element number 2. So 2 times 2 is 4, plus 0, that's, we have index number 4, then index number 5, then index number 6. Okay, so remember the indexes is one less than the nodal numbers. That's what we've done so far in the course. So I think the book also starts at 1 the whole time, but our indexes are always 1 less. So that's really what you can see here, how this global assembly works. And this is then essentially, I give it every time the local stiffness matrix that I've computed, give it the local index and give it the element number. And based on the element number, I will know where I am, what are the global indexes that are related to the element number with this inference schema. Okay, let's construct the mesh. Okay, so then the next thing is to say, construct a function that gives the global nodal coordinates, loops through the number of elements, calls the local k function for each element, and uses the assembly function to construct the global stiffness matrix. Okay, so this is essentially what this will do. So I want to have the global nodal coordinates, loop through the elements, and calls the local k function for each element, and uses the assembly function to construct the global stiffness matrix. So that is essentially what we've had. So I think this is now. Yeah, so what this does is, instead of supplying the k local in here, we essentially, with this version, yeah, here's the k local. I wanted to see where that function was. Yeah. So k local, so what I want to show you is, this is the following. Quickly find my own bearing. So what we want to do is be able to say what is the number of elements and what are the global node coordinates that we're going to be working with. Okay, so that's essentially what we have. And so what we want to do is we want to start using these functions that we've constructed here to make our life easier. So what we see is essentially, I have my k global. That will be a function of the number of nodes. The number of nodes. Because the number of nodes I can get from the global nodal coordinates. So that will dictate the degrees of freedom in this case. 1 degree freedom per node. The local indexes are 0, 2, and 1. Okay, so that's essentially how that numbering scheme works. So number 1, number 2, and number 3, like you've been used to, but it's just one less for the indexes. And then essentially we can say the global node coordinates are essentially the element number, and it starts from 0, so this range, times 2 up until e times 2 plus 3. So essentially if, and remember the last index is not included in this dot, in this sort of slicing operator. So if I want to have the coordinates, yeah, I just have a long list of coordinates. I want to pull out the coordinates for a specific element. I just say take the element number. If it's 0, then it's 2 times 0, it's 0. Up and until 3, but 3 is not included, so from 0 to 2. If element number is 1, it's 2 times 1, so it will start at 2. And up and until 5, but 5 is not included, up to until 4, so it will be index 2, 3, and 4. And so we continue and pull out the right coordinates. So this is just a list of coordinates. The global node coordinates going from 0, 0.1, 0.2, 0.3, depending on how fine we made that mesh, essentially, that we have there. Okay, so yeah, so that's, and all that we're doing then is taking these coordinates, which are now growing from 0, 0.1, 0.2, so they're ordered in terms of increasing number. We first just take the local indexes, this numbering here, 0 to 1, and create the right order for those coordinates. So that's all that we're doing. So we just create a new vector with index 0 first, what was in the second index second, and what was in the first index lastly. So that's essentially what this will do. And now we have the local nodal coordinates, because now we can start assembling our local k-local function that takes our local nodal coordinates in. So this is this function that we created here. Just takes that local nodal coordinates in, now it creates our function k-local. And once we have k-local, we can this function that does the k-global, k-local, and the local index in the element number. So we supply all of that information, and then we have the k-global with that k-local assembled. And then we go to the next element, and we repeat this process until we've gone through all the elements. Beautiful. Good. So that is essentially builds the whole stiffness matrix for us in nice chunks of steps. So we start off by first creating the k term. This k term gets used inside here. Then we can say build a k-local function where we just give the local nodal coordinates. So the other stuff is hard-coded in here. The C and the A will change. You'll have to just run this again if you want to change that. But that's essentially what that is. That's what we inferred. And then we have the k symbol. It's actually again the k local that we've just where's this? Sorry. K local is passed in here, so that's fine. So this is the symbol of k local is passed in. This creates the assembly process. And then we can say k local function using this function constructed here. We're using the k symbol function and construct everything in there. Beautiful. So this will give you a good idea of how we build this up, this complexity. And this is one way of doing it. This is not the way you should memorize it or anything. This is the way, just the way we approach and build this up. Okay. This is just to give you an example of how a typical finite element code would work. But more importantly is, this is just to sensitize you to, if you wanted to build a bit of software that's a little bit bigger than just a couple of lines, not really software, but solve a problem that requires a couple of more lines, please make use of functions, break down the complexity. This is going to be critical for MOX 14 next year, as well as MRN 4.2 next year, if you're going to be involved in anything related to some software. Okay, so then we can say problem, let's problem define solve view, number of elements, and the global node coordinates. And that's essentially how this one would work. And based on this, it would then go through this process of saying, get the node numbers, the number of nodes, create the k-global function where the number of elements and the global nodal coordinates are passed in, we have essentially a force vector, add in the tractions way at the end, the last node, partition this problem, and then solve and get the U global out. So at the end we can construct our U global as our solution. Okay, so that's essentially what we have. And again, the first index is 0, so that's why we go from 1 up until the number of nodes and get the 3 degrees of freedom out. So all the boundary condition stuff is hard-coded in this problem solved definition of solve U, so you can change the problem. You can change the area. Typically, you would also make sure you have to change the area here, that you don't use two different. What is this? No, that's fine. Yeah, this one was. The X is in the wrong. Anyway, so just double check. I see here that the areas and stuff is not 100% correct. It's 0.2 now. This is the one that's linear there. So this is not the same as that. So we can just make it like this. Doesn't matter. Let's change everything to be. You can go and change this area to be consistent. So I think at the moment this is the way the program is. That part is written there. So it's one where the area is thicker there. One edge goes thinner. So I want to make sure things are just consistent. I think I've edited it at some point and didn't pick up. I changed it a little bit. Okay, so we'll have to make sure that things are consistent. That this area is again consistent. This is not consistent with the other problem. Okay, so this will help to get that. But the bottom line is this is also important. These things don't happen. Okay, that you have inconsistent areas in the solution of the problem than what you had somewhere else. Okay. Because this is now used to compute the traction appropriately. Okay, so then essentially what we have is we have the fields for the element. So the resolution per element, how many increments would you like to define things to be plotted, the local coordinates, and then the displacement vector. And here it will run through each of the elements and do the element sigma displacement field, and this is what it will compute here essentially. It's taking the B matrix plotted with Q. That's essentially the element strain. Yeah, so that's what we have there. And then we can say the sigma is essentially the strains times this, which is just that. Compute it there. Displacements. And this is all in the psi world. And so this is essentially the element coordinates. So this is essentially every row. We create a new elements response. And then we can say the global fields, we need to now convert this stuff that's in this -1 world, in this psi world, towards the x world. And this is what this last part is doing. It's saying essentially take the local coordinates, get the correct global coordinates, and compute essentially then the displacement fields, the epsilon field, the sigma field, and all of these fields, create them as essentially as in this. Let's see, I just want to check here for myself quickly. String them just together so that you can have them in one go. So this is just creating the single row as opposed to sort of in a matrix form that we had before. And then lastly, you want to be able to plot this, so just want to make sure that we plot it. See here the area is at least consistent there. But when we go about plotting this, we want to make sure that we plot all of this stuff in the global nodal coordinates, global node coordinates, global node. So what we're building here is essentially, just to give you an idea, we're building the epsilon field. What is the epsilon field associated with each of these global node coordinates? That's what we're building there. Okay. So that's essentially what this boils down to. And once that's done, we can now go and plot these things. You can see what the responses are. Okay, so there's essentially internal force, internal stress, internal strain, displacement field, nodal displacement field, and X dimension. So this is what we have. Now we can go and say, okay, let's maybe just run it from the top. See what the time is. Maybe I should just quickly stop this. Okay, so we're running out of time. We'll stop this and then we'll play.